Hello, my name is Rick Pack. I'm one of the Vice Presidents of Research Triangle Analysts, and it is my pleasure to introduce Zan Gregg. Zan is the R&D Director of Data Discovery for JUMP JMP at SAS Institute and develops the Graph Builder component of JUMP. You can find him online at packedbars.com and on Twitter at Zan Gregg, and Zan is X-A-N, Gregg has 2 G's. I am a big fan of the packed bars data visualization that he might comment upon today. Zan has degrees including a computer engineering degree from Clemson University and has about 25 years of professional data science experience. After this great presentation, you can hear Zan in a 2017 PolicyViz podcast, easily found online. Zan, take it away.
Thanks, Rick. That was great. Talk is not about packed bars today, but I've got behind me is all the charts that I tweeted last year, and plenty of packed bar charts in there. If anyone gets bored with my content, they can peruse those graphs. Okay. So let me see if I can share screen, share desktop. Okay, so I've just got one window on a gray background. Is that?
We can see it.
Okay. All right, so I'm going to be running JUMP as this little JUMP journal for collecting some things. JUMP, if you're not familiar, is a desktop interactive statistical visualization software from SAS. Runs on Mac and Windows. And I wanted to just share some thoughts and on my favorite graph type, which is a smoother. And just do that with some interactive examples to try to understand some of the differences, the pros and cons between different types of smoothers. So let's first answer the question on why do we want to smooth at all? And for that, I thought this example from The Economist that they did last year was sort of makes a good example. They actually, at the end of the year, they sort of did a review of the graphs that they'd created and remade some of them. And this is one where they originally did it with a line chart. This is like polling results for Brexit related sentiment over a couple years. And they originally just connected the dots for each poll result with a line chart. And the remake, they used a smoother. So they still have the individual poll results as the dots, but they're now more in the background. And the smoother is there in the foreground to show the general trend. And with still having the individual poll results there, just so you have the context of how noisy the results were. But so I think it's much easier to grasp the main content. And you can still get the gist from the original, but now you're more focused on the trend instead of the daily variation. So that's sort of a little bit of the nutshell of why we want to smooth. We want to try to separate out the trend from the variation, which is the whole science of statistics, is the science of variation. Try to figure out what is the variation and what is the trend. So let's look at some ways we might smooth. I'm going to cover 4 types here. I'm going to briefly go through these with a little description and pros and cons, and then I'm going to get into some interactive examples. So the first kind of smoother that everyone's familiar with, or at least the prominent one for statisticians, is linear regression or polynomial regression in particular, where we basically are fitting a straight line or a quadratic or something to our data. And it has a lot of nice algebraic properties, not just easy to manipulate, but also easy to differentiate and integrate and handle with linear algebra. The disadvantage, which I'll show in one of the demonstrations, is this thing called action at a distance. Because it is a global smoother, basically you got one line for the whole data set. It means, a change at one end, one data point, is going to affect the whole line. So that's an issue that a lot of these other smoothers try to address, which is having more local fits. So at the other end of the spectrum is the moving average, which is the most common in the media, sort of the simplest. And we're seeing that a lot with COVID data because the world has sort of got introduced into noisy data, and that's become common to have a moving average. There's still lots of different variations of moving averages. You can have them be have the interval that you're averaging over be centered on the data point or trailing the data point. And trailing is more common. I guess it's simpler, and it also can go to the end of the data without any kind of adjustments. And you can also choose the weighting, even though, as far as I can tell, most media plots use a constant weighting so that every point in the interval gets the same weighting. But you can have a triangular weighting or some other fancier weighting. Exponential weighting is also common in some fields. I did want to show a little example of one of the disadvantages of the moving average, or artifacts, I guess you could say, and that's when you have a spike. This is from some COVID data. You end up with a plateau that lasts as long as your interval. So basically, this spike is being spread out across the interval, which, and I guess it's impossible for the smoother to know what's causing the spike, but in this case, it was apparently a backlog. So if anything, it should be credited to the previous days, but that's not going to happen with this lagging smoother. The other issue with a lagging smoother is I guess by the definition, it's lagging. So it's not, when you're going up, it's going to be trailing. So the line up is sort of lower than the data points, and the line down, going down the slope, is higher. Or in this case, it's toward the maximum values instead of right in the middle. So you might, we saw this a lot with some of the really high ramped up COVID climbs, where the moving average didn't look so bad because it was trailing moving average, so it was always a bit lagging. So those are some of the issues that the moving average has. Okay, so let's get into some fancier things, and the first one is a Spline Smoother, which is the default in Jump Graph Builder, and it's, I guess, my favorite since I used it a lot. But it's basically it's a bunch of cubic fits that are all splined together. My colleague Dwayne Hayes did a blog post about it, which is so here's some data with a Spline Smoother applied. And it's basically a bunch of these cubic equations, and they're all they're all basically a bunch of independent cubics, but they're constrained in a way so that where they meet at these knot points, the dashed lines, they have the same slope and the same x or y value, so they can be stitched together. And then when you stitch them together, you get that smoother. So it's it sounds like a lot of work, but it's it's all done by the magic of linear algebra. You basically got all these constraints being solved at once, and so it has that nice property in that it's a little more rigorously defined than some others that we'll get into. So that's a little bit on the Spline Smoother. You notice these dotted lines; these are called the knot points, and there's some choice about where you put the knot points. In this case, if there's not too many data points, you can just put a knot point at every data point. But if there's too many, you have to create some strategy of whether they should be equally spaced or trying to follow the data density. So there's still lots of choices there. Besides, I forgot to mention, there is, normally you think of these as having a single parameter, which is called the stiffness parameter. So you can control how stiff this is, but there's actually the knot points you could also think of as hidden parameters. So let's get back to Jump. So I think the pros and cons of this one are the same, I think. It's always smooth. I mean, it's a smoother, so you want it to be smooth, but on the downside, it's, if your data is not smooth, if it's got a sharp jump or something, you're not going to be able to capture that in a Spline Smoother. Though I guess any smoother is not going to do great at that, but being a smoother, but that's something to be aware of. Okay, so let's go to the next one, which is I'm going to call loess. So there's lots of different ways to spell it and pronounce it, apparently. It was originally loess with a W, which stood for locally weighted scatterplot smoothing. It's invented by William Cleveland, and I think the scatterplot smoothing has sort of been dropped as part of the name, but it's important to keep in mind that as the origin, because this was really meant to be a way to try to follow the path of the points in a scatterplot, as opposed to, it's not meant as a modeling technique or something to create a model for your data for prediction or anything like that. It's just trying to understand where your data is going. And so he created it with that name, and then later he discovered there's a word, all lowercase, which is just describes a geological formation, which is sort of a smooth hillside. And let's see if I can get that link up. My colleague Elizabeth, who I think might be on the call, has pointed this out to me, that there is a place called the Loess Hills, it's pronounced there, in the US, which has this kind of formation. That's what it is. So you can see the smoothness there. And you can also see that there's lots of different pronunciations if you know the IPA system. There's like less and loess and less. So there's so different people use different pronunciations, I imagine, but I'm calling it loess. It makes it a little easier to distinguish than less, even though less might be more correct. And so after that, William Cleveland started using that name, and a lot of times he would do it lowercase, but other people, or maybe him, started using the backronym with all uppercase loess, and started calling it local regression, which is fine, but it does sort of leave out that scatterplot smoothing angle, which is a little bit of a concern, but just because people might think it's more of a modeling method. But in any case, so how is this created? I made a little example here. It's basically a lot of little fits. So let me see what this is. The final smooth data. So it's data, and the gray dots are the raw data. This is actually a data set from Cleveland's book, and the blue line is the Lois Smoother. So that the construction of it, I think this is an example. Yeah, so it's basically a lot of little local fits. So that's the idea of the name there. So it's a lot of linear local fits in this case. And each local fit is just looking at a small band of points, and even within that band, the points are weighted, so the points in the middle are weighted higher. So we can just step through these, and you can see the different fits highlighted. So basically, you're looking at each interval, you do a fit, you take the middle point and keep that, throw away the rest, do another weighted fit, keep the middle point, do another weighted fit, keep the middle point, do another weighted fit, keep the middle point. And you just keep doing that, and then you connect those middle points in some method, which is another option as far as how smooth you do that. And then you get the final Lois Smoother. So it can sort of follow some of these local trends of the data and do it in a somewhat rigorous way. It's using linear regression, but it's still can handle local variation. So that's how the Lois fit is constructed. This local fit, I've shown it as a straight line here. It could also be a quadratic or cubic, and this weighting function is something called a tricube. But any weighting function that has a peak in the middle works fine. It could even be a normal curve that goes to no end, but most of them are defined like up to the interval of the nearest so many points. Okay, so that's a little bit of what loess is. Oh, and there's also this Robustness Pass. I always forget to mention, which is part of the original description that some people leave off altogether, but it's basically the idea was, since this was a technique for exploratory, looking at data, you want to have some mechanism for de-emphasizing outliers so they didn't affect the trend too much. And so that's what these robustness passes are. So basically the whole process I went through to get a curve, you do that, then you take the residuals and you look at the median of the residuals and use that to determine what an outlier is, and then the outliers get downweighted. And then you do it again. So you apply that global reweighting over all the data, and then you do the whole process again. And as Cleveland originally described it, you're supposed to do this indefinitely until things stabilize. But he mentioned they usually stabilize after 2 or 3 passes. So all software I've seen just makes you indicate how many passes you want up front. So I guess I haven't seen it all, so maybe there's some that do the indefinite approach. So that's a little bit of info about each one, but now let's get into some actual data. Well, this is artificial data, but to start with, just some random X values and then some Y values that I've made fit together this function, which is a ramp, and then a flat period, and then a drop, and another flat period, plus an outlier. So this is a spline smoother. You can see it's sort of picking up the outlier a little bit, and we can control that global smoothness parameter. So if we make it more stiff, we basically get a flat line. But we can make it less stiff, more flexible, and you can start following the data very closely. But no matter what it ends up with, like I said, it's always going to be smooth. There's no sharp corners, which means it can't quite get this step as looking like a step, which is okay. It's a smoother. I guess its job is to tell you that there's a step there, and you should probably be using a separate fit for this set of data points. So that's a little bit of the spline. We can try loess. We call it local kernel and jump because we've generalized it a little bit with some more options. But the first thing you'll notice probably is that it wasn't affected at all by that outlier, and that's the robustness passes. If we turn off the robustness, we can start to see it follow the outlier a little bit, and we can change the that bandwidth. How many points you're looking at, you can control that. That's the main parameter. So we can see if we make it thinner or thicker, how that affects things. And you can also choose what the local fit is. Don't expect it to matter much here, but if your data has a lot of peaks and valleys, then a quadratic fit is going to have an easier time following those. So that's loess and the moving average. Here's that plateau effect that I mentioned. In this case, it's a centered moving average. But if we change it to a trailing region, then you can sort of see what I was mentioning about how it's the up slope is not going to be followed as well because it's the trailing nature of the computation. Okay, so that's a little bit on the toy data set. Let's look at some real examples. Here's a chart from NASA that actually is using a loess smoother at the red line. This is sort of combining both cases that we saw with that economist view. They've got the before and the after in one chart. They've got the connected lines with the black line connecting all the points, and then they've got the red line with the smoother to see the general trend. And so this is, I guess that's NASA being NASA. They want to be extra precise and cover both. But it's still good to see the smoother there. It's sort of that same data set. It seemed like Washington Post did a version of it, which is a little cleaner. And it's the same kind of thing. I didn't mention the data, but this is like a global temperature anomaly over 100 years. And they sort of applied that technique that the economists did, where they have the smoother in the foreground and the dots in the background, just to show the variation in the actual data, but they're more for context. Though they did switch the smoother being for general media, I guess. So now they're using a 10-year lagging moving average. And so it's going to have that effect where it's sort of behind the data when it's moving up or down. In this case, it seems really out of sync with the data just because of that 10-year lag. And this one has another issue, or at least it did for me. I don't know if other people misread it the way I did, but I didn't even see these dots as part of the data. I thought it was a sparkle icon or something. And it's partly because of the lagging, because this is, if it weren't lagging, it would be going through the dots. And the other reason is, I guess they were intentionally trying to go for the off the charts effect, but perhaps by using a different color as well, it was too much for me to take in. In any case, that's a couple smoothers seen in the wild. I think I've got that data, or here's my spline version anyway. I'll just show that and spend more time on the other guys. So this is a spline that goes through the data and so doesn't have that lagging problem anyway. Maybe I will try to show that because I think I've got this data. I can bring it in. Forget which one it is, but I did want to point out that with the smoother, I think maybe one of the drawbacks of using a smoother that is a reason a lot of statisticians are going to be sticking to linear regression and polynomial regression is because you have to make a judgment call about how smooth do you want to make it. Do we just want to make it pretty stiff and just see, just emphasize the general global trend or long-term century trend, or do we want to try to get the decade kind of trends, or the whatever this is, 25-year trend, or do we want to really get the sunspot trend or whatever this is? So you have to make that choice, and maybe that's something that people shy away from. But whereas in polynomial regression, your choice is it's just what degree polynomial to use. Okay, this one is one that came up a couple months ago. This was something I saw on Twitter, where David Robinson, this big R data scientist, he tweeted this, which is commenting on this paper, which was studying the virus detected in sewage and whether that could be used to predict cases. And there seemed to be a lot of issues with this paper, but one of them he pointed out was one of the graphs is cut off, so I think I've got another one of those. But he was pointing out that this red line doesn't seem to be respecting these red dots up here, and he's even wondering if the outliers were removed from the analysis. This is a loess curve, and he tried to make his own loess curves and couldn't get any to come out the way theirs were. But the answer, if you remember from a few minutes ago, is because of the Robustness Pass. The Robustness Pass sort of de-emphasized these, which is probably not what you want to happen in a lot of these cases that we're seeing with COVID data, where the outliers are not really bad data or miscoded data. It's actually real data, and you need to take that into account in your model. So let's we can try to reproduce that with that data and jump. So just look at the red data. I think it's this data. So there's a spline smoother. It's sort of given some attention to those outliers, but if we go back to the loess, it's going to be less attention to it because it's got the Robustness Pass in. I think theirs was a little smoother than this. It was probably more like that. And then if you turn off the robustness, though, you can see it does get back to that, a little more respecting those high values. And so I think a part of the issue was they were using different bar packages. You know, there's one loess with a W and one loess without a W, and one of them has the robustness pass on by default, and the other has it off by default. And so that you know, researchers or that may not even have been aware that that was happening, but it is something to keep in mind that that is a part of the loess definition. So I think those two packages support it, but have different settings. I think ggplot will also use a loess smoother, but it does not even have an option that I could tell to turn on robustness. So that's you know, something to be aware of for that for sure. Something a little more positive note is this data I saw on the ozone thickness. So this was tweeted about you know, trying to celebrate the success of the Montreal Protocol in the late 80s to reduce the pollutants that were causing the ozone thickness to go down, and they were pointing out how things had leveled off and stopped going down since that went into effect. I wanted to, you know, I was wondering, you know, how this would look with a smoother, because you know, all these up and down lines are a little distracting to me and my little brain, and also this this big blob in the background, which I didn't realize what it was at first, but it's the Earth and South Pole, and so they've overlaid this kind of rainbow heat map over it, which was, I think, also interfering with my ability. So I got that data, and this is actually a couple more years than that chart has. Let's look at that. I think minimum, yeah, thickness. Let's see. Yeah, this is the thickness. Okay, sorry. All right, so this is the smoother for that data, and it actually looks like it might be going up a little bit. That's you know, which is something that was not apparent if you just look at the line chart. Just click on the line here. Just look at the line instead. So it's, I mean, you can look at it, if you look at it carefully, you can sort of see, oh yeah, it is sort of inching up a little bit, but it's not so apparent as with the smoother. So I think that's a win for smoothers, and it came out with a decent stiffness by default, but we can control that. And as before, one thing I just wanted to mention, one thing about smoothers is there's not always a well-defined confidence interval or prediction interval. I mean, there is one defined, at least for splines and loess, you can get them, but it's, you know, much hairier. What we do here is we have this confidence of fit, which is basically using a bootstrap. So it's basically doing several hundred fits and then taking the inner 95th percentile that you would get, similar to effect if you did like a spaghetti plot kind of thing to understand the confidence interval. So it's going to move around a bit since it's a random bootstrapping. But one thing I like about it is that it's, I think when you start overfitting, you can sort of tell that the line is bumping up against the edge of the confidence interval, and you can sort of, I think if you have, basically if you can draw a straight line through the confidence interval, then your curve should probably be straight there too. So it's a useful diagnostic, I think, even though it's not as, you know, a lot of people would prefer to have a prediction interval, which can be useful in other situations. But in any case, that's a little bit about confidence intervals there. And the final data set here is this one that just came out yesterday about the Belarus vote, or presidential vote they had last week or so. So I just found this data set, which is like about half the precincts. And if anyone knows Russia or Belarus or whatever language that is, these are, I think, precinct names. And someone pointed out a few anomalies in the data. So let's look at that. I think maybe I've already got that one in one of these scripts. Yeah, so this is basically, they thought maybe the early voting areas had some discrepancies. And let me make these dots a little more transparent just to help see the um, there's a few areas where there's just a big cluster of values with low value. This is a percent voting for the challenger or the main challenger. There were several people in the race. But in any case, there's some anomaly here, which you can see in the scatter. I was sort of interested, but just because of the way the different smoothers pick it up. So here's a spline, and you can sort of tell there's a bend in the slope. But which is not too surprising anyway, because it can't keep going past 0, so it's going to start leveling out. So the spline is actually not really being that informative, I don't think. With the loess kind of fit, you can get to a point where it sort of shows a smooth curve with a noticeable dip. So it seems to do better in that case, I think, because this data is so dense here, and the loess fitting is based on the basically nearest neighbors, instead of a fixed interval. So I think that helps there. One of the generalizations that we have here, is not just picking a quadratic, but we can also pick a median for the local fit. So that was sort of telling, because it really can follow that data pretty well, I think. And this was invented, I think it was in the 80s, for the whole loess technique by Cleveland. But before that, John Tukey had a technique called a wandering schematic plot, which was, you remember, he called the box plot was originally called the schematic box plot, and this is the continuous version of that, where he had the median, sort of a moving median, tracking the data. He didn't, have the computing power to do it, completely moving median. He basically created like 10 box plots throughout the data, sort of partitioned the data into slices, and then did 10 box plots, and then connected the median and connected the quartiles and so on to get that moving. And we can do that. We've got that called a moving box here. So this is basically the same idea. There's that same moving median in the middle, plus the quartiles. So that's the Tukey wandering schematic plot. So yet another variation on smoothing. So finally, I wanted to show a bug in loess, which I discovered while doing development. And I made a observable notebook to illustrate that. And it's using, ironically, the data set that was in Cleveland's book, which is basically 3 curves that are stitched together plus random noise. And what I noticed as I was doing my development and explorations was that if the noise was not very much, basically which happened if I forgot to add the noise, you get these really strange artifacts here that look like the smoother is definitely not working. And it took me a while to figure out what was going on. I thought there was a bug in my code for the longest time, but then I realized this, I tried it in other programs. It happens in R, it happens in SAS, happens in JavaScript, which is what this is. So it's really a bug or a feature, artifact, whatever, in the algorithm, not in the implementation. And it's from the Robustness Pass. The Robustness Pass is basically, it tries to figure out what's an outlier. And so if we turn off the robustness iterations, we can see, it's not so bad. And this is basically what the first pass looks like. And then after it makes this pass, it's going to look at all the residuals, which are very small in the tails and very big in this peak and valley. And then it's going to decide, what's an outlier or not. And it decides that these are all outliers because the median residual is very small, the median absolute residual. So everything else looks huge by comparison. So basically, these are going to get ignored. And so when it's trying to make its local fit in this region, it's going to be ignoring all these points, and it's just going to be looking at these points and these points. And so that's why the line is basically going through there at that point. So that's a little bit about that sort of flaw. And I've made an adjustment within JUMP, is what we're proposing, and one of our statisticians is working on a write-up. It's basically, instead of using 6 times the median as the cutoff, which is what Cleveland did, basically saying anything beyond that is infinity away, just ignore it. We were trying to figure out how to adjust the rule to sort of capture that spirit. He still wanted to have a cutoff, but as opposed to, we also looked at some other things that had no cutoff, just continuous degradation, like a Hoover kind of distribution. But we tried to maintain the spirit, and so we also we mixed in 2 times the 90th quantile, which is if you have a Gaussian kind of distribution of residuals, then that's going to be less than 6 times the median. But if you don't, if you've got this weird case where most of your medians or most of your residuals are near 0, you'll have a better chance. So now you need to have 90% near 0 before you encounter that flaw. So that's what we've been working with. And so here's a JUMP version of that same kind of thing I showed in observable. I guess I better turn on robustness just to make it a fair fight. And so you can see now if I make the noise very low, it's not going to be troubled. And just to reference what I said earlier about, sort of the linear fit not hitting the peaks as well. If I make the bandwidth smaller, it can hit them, or you can make the fit a quadratic, and that'll work with a wider bandwidth. So that's what we're shooting for, and that's my quick tour of the smoother world. Hope you guys can start smoothing some more, or have a better appreciation for different kinds of smoothers. And that's all I got. I'm happy to take some questions or have some other discussion later. Thanks.
Thank you very much, Dan. There were a number of questions about different tools. So you showed JUMP and observable, which I guess that's D3 JavaScript.
Yeah.
Some folks wondered in the Python world, R world, if you have any favorite tools for for smoothing specifically.
Oh, well, no, I don't. I mean, I only know the sort of the standard packages. There's one called loess, or there's 2 as I'm called loess, one with a W and one without. One without, I think, is more recent, but I think they're equivalent, except for some other, various options. And yeah, so that's all I'm familiar with there. Yeah. There are lots of other smoothers besides these in particular, I guess I should say, but I haven't worked with them as much. It's Gaussian process kind of thing, which is more useful for high dimensional data.
All right. Anyone else want to go off mute and ask a question?
Yeah, Zan, a few years ago, we had a presentation by somebody from SAS who was showing us his Spline Smoother, Spline Fitter.
Okay.
I don't remember his name, but I was wondering if JUMP was using his library.
I don't know. I mean, there was, well, I guess if it was recently developed, probably not. JUMP and SAS have a lot of common core statistical, function library, but they were sort of forked, 20 years ago or so. But I don't know what, what would be different. I guess the main research, I guess, has been on how to extend Spline to higher dimensions without becoming a performance nightmare. So that may have been what he was bringing.
Yeah, he was talking about how expensive it was from a compute standpoint to get that to work, and how he was able to constrain the algorithm, constrain his algorithm to make things work within a lifetime.
Okay, yeah, it may have been for the higher dimensional data then. But it's worked very performant for me for 2D data. Even with millions of data points, it's just linear algebra, which is what computers are good at.
So we had another question in the chat from Mike, and it's, have you run into and considered asymptotic methods and perturbation theory? Its intent is to find a series which can be made as close as possible to approach the same function without the infinites existing in the original function.
No, I don't know what those are.
And then I had one question. It seems as if in a lot of tools, smoothing is implemented in the visualization layer. And I wondered if you think that that could be a problem for like reproducibility and things like that. Like, do you have any thoughts about whether it ought to be implemented more as a data step as opposed to in that final visualization layer?
I don't know. There have been some issues with that getting in, with causing some trouble. I mean, I think I guess I feel like we shouldn't be smoothing too early, because a lot of the statistical methods are designed to handle variation, and you don't want to get rid of it before doing the modeling or something. So that was that'd be my main concern. But yeah, there are there's, at least for the Spline Smoother, you do get a closed form expression out if you create the curve. I mean, it's a big expression. If you got 50 cut points or knot points, then you basically got 50 cubics that are fit together, which is basically a big 50 by 4 matrix that has to be evaluated for each point or along the curve. But it's not so readily computable for a loess kind of thing. Basically, all you can do is record the points in the curve and then apply an interpolation to get sort of a model out of that. But yeah, it does feel to me more for exploratory kind of thing. I think, well, at least for me, I think it sort of leads to suggesting how you might model things, like in that ozone example where it sort of went down and then started gradually going back up. You can sort of imagine that as a mixture model with the pollutants were having a downward effect, and then there was some other natural process maybe that was causing it to reach some go to some natural stable point, and then those were weighted by the law regulating the pollutants, the Montreal Protocol, and so you can see how they mix together to create that curve. Even though which is something that you could use for prediction outside the range, but the smoother itself, I wouldn't want to use it for too much prediction. I mean, I think your question is a little deeper than that, but that's what comes to mind anyway.
Great, thanks.
Can I ask a question? I enjoyed your presentation, and I noticed that all your examples were two-dimensional. I've seen smoothers work in kind of three-dimensional data, but do you have any commentary about using smoothers in kind of 3 dimensions to 10 or 15 dimensional data?
Yeah, I think, well, these methods generally don't scale so well to that. That's what I think Mark was getting at with the spline, where it's a bit challenging to use something like a spline smoother for that dimensional data, and that's where I see Gaussian process as the dominant smoothing method there, which is basically, I mean, it is similar to the loess in a way. It's sort of doing these little local kernels all over the multi-dimensional surface and sort of mixing them together.
All right, there's another question from Elliot. Do you have experience with data visualization and data storytelling? as you showed, smoothing these data points can significantly change the interpretation of the data. The algorithms for doing smoothing are fairly complex. Do you have any general guidance for how you describe smoothed graphs for a data story intended for the general public?
Well, I like to, just, maybe use the word trend, or say, say it's not really say it's, like the, it's not the line of fit or anything like that. It's really just the general trend, and it's sort of where the data is going. It's not necessarily saying what's underneath and what's causing it. It's just sort of showing where it's going, and then it's up for us to figure out what the reasons might be. I think that's part of the reason why a lot of the smoothers we see in the media are very simplistic. Just the moving average, which is still a choice that's made, and but it's just easier to explain what's going on, even if it might not be as effective at capturing the underlying trend.
Okay, and we have one more question from Ron, and he says, I was using a moving average on a waveform and noticed that it reduces the slope, compared to the raw data. Is this sort of inherent in all smoothing methods?
Well, it's hard to say all, but yeah, it's definitely going to happen in a lot of smoothing methods. The moving average or the loess with a linear fit is never going to go beyond the bounds of the data, because it's taking the midpoint of that line that fit the region. But if you do a loess with a quadratic fit or a cubic local fit, then it can have a it can follow the full range of the data and even exceed it if that's if the data is structured in just the right way. So at least that technique, the loess with a quadratic fit or a spline smoother, can follow the full range of the data without that issue that you were seeing. But yeah, I think that's always going to be present in a moving average.
All right, last call for questions before we let Zan go. Well, there's one final question from Mike. Should we, as data scientists, be doing smoothing or even modeling on a process without a theory that relates that model? In other words, shouldn't we do smoothing and prediction with an idea of the underlying process that's producing the data?
Okay, yeah, that's a big question. My view is sort of like the exploratory data analysis, approach behind loess that Cleveland first talked about, which is basically just trying to see where the data is going and give us ideas for, what the model might be. Like I mentioned in that ozone layer model, it might give you an idea if there's two, at least two parts here. One that's a negative part, and one that's a positive part, and they're showing themselves in different degrees over time, or something else going on. You might decide these two things are really categorically different because there's a big jump or something. I think it just helps spot those things. I know there's a there is a big philosophical issue there with statisticians as far as making your predictions before you start wading into things, or whether you should try to wade into things and get ideas. But I can't, I'm not going to find the answer to that. But I think there is a role there.
All right, well, we'll invite you back for a TED Talk, maybe in a future meetup on that topic. But
Okay.
For this time, thank you very much, Zan, for your insightful talk. Thanks everyone for the questions and discussion. We will share the recording within a week or so. You can check our social media channels for that, and I think we'll also post a comment to the meetup with the link to that recording. Thank you very much, and we'll see you next time.
Thank you.